Okay, so today's session, we're going to first review the tutorial questions, okay, of the last few studios, and then we will look at the some of the sample questions in the tutorial that was added in, okay. So I think those of you who attended Colin's session on Wednesday may have already gone through some of those questions. Okay, so for the benefit of those who did not attend, we will still go through those questions, okay? And then we'll go through the SOP as well, okay, just to make sure everybody is clear on what you need to do, okay, for tomorrow's quiz. Okay, so let me get started with the tutorial questions first, okay, and then later we will switch over to the PDF file with the practice questions. Okay, so all can hear me? Any issues? Can see the screen? Yes, no? Okay, thank you. All right, so I just want to be sure before we carry on. Okay, so thank you. Let's get started. Okay, so the first part of the tutorial is on timers. Okay, so timers we saw in the earlier studio as well when we used it for PWM. Okay, and then later on we also introduce you to the other mode of operation, the CTC. Okay, so the idea is timers in general can be used for a wide variety of applications. All right, so PWM is one use case, and using a timer to generate periodic interrupts is also another uh, uh, commonly used option. Okay, so in this question here, we are talking about the timers. Okay, and we are asked to look at the sections 19 to 22. So those sections are basically the sections where they explain to you about the timer and how it operates. Okay, so that part you can go through, okay, and read for yourself. Okay, so for this question here, give two examples of use of timers. All right, so of course, the application wise, yes, we have seen the PWM, okay, as a way of using, as a way of applying timers. Uh, in other cases, you can say that if let's say your system wants to implement a real-time clock. Okay, so a real-time clock is basically what we call it RTC, is to keep track of time. Okay, from the moment you power up a system. Okay, in some systems, this real-time clock will be running at maybe even a very finer resolution every millisecond or every microsecond to keep track of how much time has elapsed since you power up the system. And in like if you take your laptop for example, okay, even if you plug out the power and you remove the battery, right? If you remove the battery, okay, and after a while you plug in the battery again and you power on, you will still see that the time is updated correctly. Correct, the time is still updated correctly. Okay, because in different kind of systems, they may implement a separate hardware-based RTC. Okay, that means even though the processor may have RTC running, okay, you can implement a separate RTC which can be powered by a battery, which is not your main battery that is powering the rest of the system. Okay, so you may have smaller kind of a coin battery, okay, somewhere in the system to just power the RTC. Okay, so different type of systems may implement this real-time clock sort of feature, either in software or in hardware. All right, so this is one example where you can use timers to give you periodic interrupts. In a module that you'll be doing next year, which is my module 2271, you will be learning about operating systems. Okay, and in that module, you will also get to see how timers are used, okay, to switch between tasks. Okay, so when you have multi-threading, we will talk a bit of multi-threading later on in the last part. Okay, but when you learn about it in more detail, you'll see that you can write several uh, parts of the program, okay, and everything can run sort of concurrently. Okay, in our current context, we say that we have a main loop. Okay, we have a main loop, and that main loop is running, and the thing that deviates from the main loop or the normal function call is our interrupt. Okay, you service an interrupt and then you can go back. With multi-threading is a bit different, or multitasking, where you can have multiple tasks running concurrently, okay, and all of them will sort of share the CPU. Okay, so these are things you will learn next year, okay, in 2271. Okay, but again, this is just to show you that how timers in a processor are actually used. Okay, in what we have seen so far are timers 0, 1, and 2. Correct. We have seen the application of both the 8-bit timer and the 16-bit timer in our studio so far. Okay, so when we say is an 8-bit timer, okay, so what does it mean? Okay, so it basically means that it counts, okay, from 0 to 255. Okay, so that is the limit. And if you look at your data sheet in terms of the prescale values, okay, so these prescale values are of course fixed by the hardware itself. So depending on what, I mean, you have the options are fixed in the hardware, and then you configure the bits to select the option that you want. All right. So the largest resolution you can get is if I divide by 1024. That means that is the slowest at which I can clock my timer. All right. So if I run at 16 megahertz, then the number of cycles between increment is 16 megahertz divided by 1024. That will give me 15,625. And that translates to around 0.000064 seconds between increment. That means when I go from 0 to 1, okay, that is the amount of time it takes this time here. All right. So if I were to look at the full range or the full scale, you can say that it will go, the largest interval will be from uh, this number multiplied by 255, which is about 0.0163 seconds. Okay. So you can see that even with the slowest clocking interval, okay, the full timing delay that I can get between interrupts. Okay, that means if I were to trigger that the interrupt happens every time I overflow, then it will be only about 0.016 seconds. All right. So that is still quite fast, correct? The rate at which it will interrupt. That is where you can say that the timer one, which is a 16-bit timer, actually gives us an advantage, because if you do the same calculation, okay, with 16 bits, okay, and that per count takes this amount of time, but with the 16 bits counter, your range is much larger, correct? 0 to 65535. All right, so the maximum interval is now 65535 multiplied by this, which is 4.19 seconds. All right, so it is now possible that you can have interrupts at 1 second interval or 2 second interval or so on. All right, so that is the advantage of a 16-bit timer. Of course, if you look back at the earlier studio that we did, earlier tutorial, using the 8-bit timer, you can still uh, have larger sort of interrupts or events that you can capture, but you need to keep track of that separately in your ISR, correct? So if you remember, there was one slide where we said that if I take one complete, every time I trigger the interrupt, that interval in this case is, okay, 0.01632 seconds. All right, so every time I trigger and jump to the interrupt service routine, okay, then I increment another count variable. Okay, so that count variable will be basically multiple of the 0.016. All right, and that can give me the desired interval. Okay, but I need to keep track of this shorter interval using this additional variable. Okay, so this is of course another technique you can use if you do not have a higher bit timer. Okay, but in our 8328 we do have a 16-bit timer. Okay, so we can use that. Okay, so what is the disadvantage? Okay, so I don't think it's a big disadvantage. It's just that since you're dealing with an 8-bit system, all right, all your registers are 8-bit. So when you want to configure, in most cases, you need to do a bit more configuration, all right, to set things up. Okay, but other than that, there's no major disadvantage. Occupying more space has to be correct, because if you want the convenience and the advantage of a 16-bit timer, then you need to have more space to accommodate. Okay, so in this case, the more space is just talking about the additional register to hold the values and to do whatever necessary configuration you need. Okay, so I would say it is more having it is more of an advantage than a disadvantage, because you now have that option, okay, to utilize this timer in the event that you really need to have larger intervals. Okay, so that is question one, just to give us the idea of 8-bit and 16-bit and how we sort of compare them. So in question two, we are basically given these register contents, okay, and we are told that the OCR register holds a value of 247, okay, and we are operating the timer one in CTC mode, okay, and the all interrupt flags are already properly set, okay. So these are the configuration that has been written to these registers. So what do these bits mean? Okay, so it's important that you are really comfortable looking at these bits, looking at the information in the data sheet, and knowing how to relate this information, correct? So you should be able to look back and say, okay, this first two bits here and the other two bits here are relating to the behavior when there is a compare match, correct? Should I set high, set low, toggle, and so on, right? So that part is the first 4 bits, okay. And for timer one, to set the mode of operation, there are 4 bits, all right. So those 4 bits are split into the 2 registers, the A and B register, all right. So the lower 2 bits come here and the upper 2 bits come here, all right. So you have 2 parts to this, all right. And when you look at it together as the 4 bits, you see that this mode of operation is what we call the CTC mode, okay. And finally, the last 3 bits of the 1B register give us the prescale value. Okay, so these are the things that you need to take note of, all right, when given the contents of a particular register used to configure a peripheral. Okay, what do each of the bits mean? Okay, so what is the interval between which timer one interrupt is triggered? Okay, so we know that the prescale value is 256. Okay, so the period at which you will increment your counter is 16 microseconds. Every 16 microsecond, you will be incrementing it. So the period is, if you look back at the formula that we'll be using, is 247, okay, plus 1. Okay, 247 is the value, okay, that OCR is holding on to. Okay, so it's 0 to 247. Okay, so it is 247 plus 1 multiplied by 16 microseconds. So you get interrupt interval of 3.968 millisecond. Okay, so these are all, I think, things you are familiar with, correct? We have been doing this in the studio as well. Okay, so in terms of the waveform, so you can see that since the COM1A 0 and 1A 1 bits are 0 1, okay, the operation means, I mean, this configuration tells us that we want to toggle on match. So when you say toggle on match, means every time there is an interrupt, we will toggle, okay, on this match, and that is giving us a waveform of this 4 millisecond up, 4 millisecond low, okay, high and low, so total of 8 millisecond. All right, so I think what you must understand, which you also we look at studio, is this behavior of the pin, all right, is separate from the interrupt. Okay, we can configure the interrupt and not configure the pin to behave in any particular way, correct? That means I can say that I want the interrupt to happen every 4 milliseconds, but the output compare module is not going to affect the actual digital pin. All right, that means I will still trigger, okay, and then I do not do anything to the particular pin. Okay, so the COM1A 01 A1 will both set to 00. Okay, and I can choose to generate this waveform on any IO pin, correct? Any IO pin. So the toggling of the waveform, all right, can be done on any IO pin. Okay, it is just that it is more convenient to use the pin already tied to the timer block, because then you don't need to worry about it, because the moment you set it up, it just happens automatically. Okay. If you don't use the pin that is already tied to the block, then inside your ISR, you need to go and manually toggle the pin, or change the value of the pin and so on. Okay. So you might always remember that they are two separate things. The interrupt is one thing. Okay. The pin behavior is a separate thing. All right. And once you configure it, all right, you can configure it that it just happens automatically all the time as long as the timer is enabled. Correct. Okay. So we saw that for the PWM as well. You don't need to keep resetting all the registers or whatever. The moment you configure them once, all right, it will just happen. Okay, because it is a hardware driven peripheral system. All right. So once everything is configured, the behavior of the pin will just happen. Okay. Unless, like what I said, if your intention is to use a separate pin and not the pin that is tied to the block, then inside ISR, you need to go and manually change the values accordingly. Okay, so that is the flexibility you have. So it's not that you are tied down to only using these pins. You are free to use any pins. It's just about whether the hardware supports it or you have to write some software to support it. Okay, so in question 3, we are told that we want to trigger timer 0 interrupt every 650 microseconds in Ctc mode. Okay, so we are given a table, okay, and we are asked to fill it up, all right, and we are told that in this case it's run at 20 megahertz. So again, these are things that you should take note of, all right, when the question is being asked. Uh, though we are used to using 16 megahertz because our board is 16 megahertz, okay, it's easy to just change the question and say it's running at 2 megahertz, correct, or 10 megahertz. Okay, so look at it carefully to see whether it is mentioned, if there's any change in the frequency, all right, that you need to take note of. Okay, so since we, to get the period, that means the rate at which you are going to update the counter, you take the prescaler value divided by 20 megahertz. So of course the table has all the prescaler values. Okay, so we are just going to go through one of the prescaler values. So the first step is uh, prescaler value divided by the frequency. So this tells us the rate at which the counter is going to increment. Okay. So in order to reach 650 microsecond, you divide it by 3.2, so you get some value, and we are told to do a round up. Okay, whatever value you get, we are told to do a round up, and if we get, so in this case from 203.125, we do a round up to 204. Okay, so we get a period of 204 times 3.2. Okay, so that is the actual period that we get. So this is 652.8. Okay, and we wanted 650, correct? So there is an error of 0.43% over here. Okay, so again, this error will always be there unless you get a perfect multiple, correct? That means the rate at which you increment the counter, which is this, can multiply by a number and perfectly give you the actual rate that you want. Okay, but in many cases you may not get the actual number. Okay, so there will be some error you need to deal with. Okay, so that same sequence, if you go through for all the prescale values, so you will see that for these two table entries, the B value is not written because it's too large, all right, because you need to fit into an 8-bit register. Okay, it's too large to fit into an 8-bit register, so it's not possible. Okay, so that is where you have the other three possible prescale values: 64, 256, and 1024. Okay, so based on the table, which value gives us the best accuracy? So we can see that both 64 and 256 give us the best accuracy, whereas the 1024 gives us a lot more error. Okay, so this is quite intuitive, right? The smaller the prescale value, that means I'm able to increment at a shorter timing interval. All right, that means it's easier for me to hit some particular value that I want. All right, and the error will be much smaller. Okay, so uh, that is where, of course, a 16-bit timer can come in, because if I have a 16-bit timer, then I can use a smaller prescribed value and hit uh, 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 hit the desired interval with close to zero error. Okay, in many cases. Okay, so that sums up the first part on the timers. All right, so let me move on to the serialization, which we just did. Okay, so for serialization, the whole idea, okay, I'm not sure how many of you managed to do until the part where Rpi was communicating with the Arduino. That means Rpi code was running. Okay, that means you compile and run the Rpi code separately, and then you run the Arduino code, and they both were talking to each other. Okay, so that part was given to you, but I'm not sure how many of you reached that. Okay, but if you actually have done only the first two parts or so, that already gives you the idea of what we are trying to achieve. Right, we want to achieve the objective of two computing platforms talking to each other. Okay, so in order for two platforms to talk to each other, you must have a protocol. So the protocol has different sort of layers. All right, that means at the hardware level they must match, and then at the software level also they must match. Okay, so later in one of the slides I'll talk about that. All right, so that you understand what we are trying to do. Okay, so even if you've not done it yet in that last studio, you will have to revisit again, because once you come back from the break, okay, the rest of the studios we're going to be going more into the inter-process communication between Arpa and Arduino and getting everything to work together. Okay, so in this first question, okay, we are looking at the parity. All right, so as what we discussed in class, the parity bit is an extra bit. Okay, and what we want is to make sure that this additional bit uh, will make sure that the total number of ones, okay, either is odd or even depending on what we agree on. Okay, so it's always important that both, okay, TX and RX both already agree on a particular parity. Okay, so it is not an auto detect and auto configure kind of system here. Okay, so transmitter and receiver separately must have already been configured with the same kind of settings, so they know how to transmit and the receiver knows what to expect. All right, so if either one, the configuration, there's a mismatch, okay, you will see that transmit side I'm transmitting, but receiver side is receiving something, but you can't make sense of it. Okay, so if you have the situation, that means something is wrong with some configuration, the baud rate, the number of stop bits, okay, parity, and so on. Okay, so in terms of odd parity, basically the total number of one bits is odd. If even parity, the total number of one bits is even. Okay, so if you look at this data over here, I have 3 ones over here. Okay, 3 ones. Okay, and if I say I want odd parity, means the parity bit will be 0, because I already have an odd number here. Okay, in the same bits over here, I have 3, which is an odd. Okay, but if I want to transmit as even parity, then this one must be a 1. So plus 1 will be give me 4, which is an even. All right, so that is the idea of the parity bit. Okay, and most I would say serial blocks have a built-in parity bit generator. So all you need to do is configure whether you want even parity or odd parity, or whether you want parity. Okay, so as long as you say you want and you decide between even or odd, the hardware will automatically generate this bit and append to your data packet. Okay, so you don't need to do it explicitly. Most systems already have built-in uh, sort of mechanism to provide this additional bit for you. Okay, but you just need to configure it in your registers. Okay, but why is this error detection not reliable? Okay, because it can only detect if I have an odd number of errors. Okay, so let's look at example. So imagine that this is the data packet I want to transmit out. Okay, and I say I want even parity. Correct. So if I want even parity, means the number of ones must be even. So I append. So currently I have 3 ones. Correct. I have 3 ones. So I add plus 1. So it becomes 4 ones. Okay, so it's even parity, and then I transmit over the channel. Okay, but of course along the way, what happens? There is some noise, there's some interference, and because of that interference, you see that 2 bits have flipped. Okay, the bit 1 over here has become a 0 over here, and this 0 has become a 1 over here. So 2 bits have flipped, and when 2 bits have flipped, okay, you will see that I still have 4 ones. Okay, I still have 4 ones. That means I still detect as correct in terms of parity. So I'm not able to detect, okay, that actually an error happened. Okay, so this is of course a limitation of the current basic parity check. So that's why we need higher levels of check, okay, like checksums and CRC. So you will actually be doing this later on, okay, when we are doing the higher level protocol between Rpi and Arduino. Okay, so in this is to sketch the frames. Okay, so we don't need to go through all. Okay, I think we just go through one or two. So if I take this data and I want to follow, implement these data frames. So for example, 8 and 1. 8 and 1 means I transmit 8 bits. Okay, so 8 bits of data. This one is no parity, N is no parity, and this one is one stop bit. Okay, so I'll have a start bit, okay, over here, plus 8 bits of data, and then there's no parity, and then one stop bit. Okay, the same thing over here, 8E1 is 8 bits of data, even parity, and one stop bit. So 8 bits of data. So in this 8 bits of data, I already have 4 ones. Okay, so I can see that I already have 4 ones over here. So it is already an even number. So the parity bit is a 0. Okay, parity bit is 0, then I put a stop bit. Okay, if I say 701 means I transmit only 7 bits. So I discard the most significant bit and transmit the rest of the bits. So for the rest of the bits, okay, when I say odd parity, you can see that for this 7-bit data, I have odd number of ones. Okay, so for this, you see that I have 3 ones. Okay, so it's already odd number, so the parity bit is odd. Okay, so and for this one over here, the same thing, start bit, 7 bits of data. So since I have 3 ones, I need to do a 1 as the parity bit, and then I do a stop. Okay, so it is quite standard the way you deal with this format: 8N1, 8E1, 701, and 7E1. Okay, so the other data packet I will not go through. Is the same thing. Okay. Okay, so just now we saw that if I were to calculate parity within a single byte, okay, it does not really help me to detect even number of errors. Okay, one possible improvement is we can calculate parity across bytes. Okay, across the bytes. So if you look here, okay, if I look at these 3 bytes over here, so for each byte I calculate a parity. Okay, and for each column I also calculate the parity. Okay, and you can see that for the row 1, okay, row 1, you can see that there is an error because I am using odd parity system here. That means I should have odd number of ones, but I have 1, 2, 3, okay, and the parity bit here is 1. Okay, so you can see that 1, 2, 3, 4. So the parity bit here is a 1, so something is wrong. Okay, the parity bit here is a 1, so something is wrong. Okay, but by right it should be an odd number. Okay, but it is a 4, so something is wrong. Then if I look in the columns, okay, you will see that this column has 2 ones, which is even number. So again, something is wrong. Okay, the rest of all the columns have an odd number of ones. Okay, so you can see that by looking at the row and the column, I can know that this particular bit is the one with the problem. Okay, so this is an improvement because in the previous case, okay, even if I have 1 bit flip, okay, if I say that 0, 0, 0, 1, 0, 0, 0, 1, correct? Okay, when I transmit over, okay, and I say, for example, even parity. Okay, when I say even parity, I append a 0, correct? So I say 0, 0, 0, 1, 0, 0, 0, 1, and I append a 0, correct? But if I receive 0, 0, 0, 1, 0, 0, 1, 1, okay, with a 0, I only see this, correct? I only see this, okay? You do not know what you transmit, but when you receive, you see this. But since it's even parity, you know that this is wrong, okay? This is wrong. But you do not know where the mistake is. You only know that there is an error here. Okay, so with the normal parity, when you detect error, you only know that there is an error. You do not know where is the error. Okay, because you only count the number of ones. Okay, but if I look at this example here with parity across bytes, when there is an error, I'm able to detect where there is an error. Okay, but again, there is a limitation because if there is more than one error in the same row or same column, okay, then again you come back to the same thing. Okay, because only odd number you can detect. Okay, with even number it comes back to the same problem. All right, so this is an improvement. Okay, but it is not uh, a very good solution. Okay, it is a slightly better solution than the previous one. Okay, so in this last question here, how long does it take to transmit all 128 bytes in a buffer and 9600 bits per second? Okay, so 128 bytes is equivalent to 1024 bits. Okay, so 9600 bits per second means, okay, if you do the calculation, one bit is 1 over 9600 multiplied by 1024, you'll get 0.11 seconds. Okay, so what implication does this have on how fast your program can write to your buffers? Okay, so what does it mean? That means you are trying to write data to a buffer, okay, and then you're trying to pass it to the UART module that will transmit out. Okay, so the whole idea must be that your UART module must be able to transmit out faster than I can write to this. Correct? If I write to it too fast and I haven't transmit out the data, okay, then there's a high chance that I will overwrite the data. Correct? Because before I can finish sending the old data, new data is already coming. Okay, and then I have to overwrite. Okay, so these are again uh, things that you need to consider where you have a lot of data to transmit across a channel. You want to make sure the channel is able to handle that rate at which the data is coming. Okay, if not, that is where you have a lot of data that is being lost. Okay, so that brings us to the last part of the questions already. Okay, so this is the part where, again, if you have not tried this yet in the studio, then you'll probably do it again after the break. Okay, but if you look at the studio handout, the last part is to establish communication between Rpi and Uno. Okay, so your Rpi and Uno are basically connected using the USB cable, all right? And in your Rpi, we have given you a separate code to run, and your Uno is running its own separate code, and they're both talking to each other. Okay, so the first thing is 3.3 volts and 5 volts. Okay, and to do that, you actually need a voltage translator, all right, to do it. Okay, but I think if you look in the handout, the Rpi is able to handle it, so we are not actually using the voltage translator. It works by itself. Okay, where Rpi itself is able to handle the incoming data, okay, at 5 volts, so there's no issue. Now the other thing is the software aspect. The software aspect is the Arduino. If you look at the code, we are using interrupts to handle transmit and receive. Okay, so whenever I transmit or receive, I have interrupts, okay, to handle the communication. But for Rpi, okay, if you look at the code, okay, you look at the code that is given to you, you will see that it doesn't use interrupts. Okay, if you look at the code, it does something like this. Okay, it does something like this. In this, basically what we do is, this is where we set up the serial buffer, okay, to say which is the port, the baud rate, how many bits, even parity, and so on. Okay, and what is here that is significant is this fork here. All right, so if you look at fork, what it does is it creates a separate process, from that point, okay, in the code. Okay, that means what happens is with fork, all right, this code here, in this code here, run in two separate threads. That means you can imagine that if this is your transmit, your serial write, and this is your receive, right? Serial read. Okay, so what is happening is your transmit and receive both are actually running at the same time because of this thing called fork. All right, so we are not going to go to the details, all right, but the idea is this is actually the concept of multitasking. That means two sets of code actually sort of running together at the same time. All right, so currently you don't see that in the Arduino. All right, in the Arduino, what you have is you have the main code. Okay, you have the main code running, and whenever you need to break away is when the interrupt happens. But even then, after the interrupt, you go back to the main code, okay, and then you carry on. Okay, you don't have the idea that it is sort of running in parallel. Okay, whereas in Rpi, what is happening is you're running in parallel. Okay, of course, this idea of parallel is again, it's not. We're not going into the details, but this is what we call the multitasking or concurrent uh, programming in a sense where you have two tasks running together, okay, at the same time. Of course, technically they are actually switching between each other very fast. Okay, so it gives you the idea that it is running in parallel, but it's actually switching between each other very fast. Okay, again, that is the multitasking concept, and that is how RPi code is written, and the code in the Arduino side is written using the main loop and then the interrupts. Okay, so as we build upon the robot, okay, after the break, you will see that there will be quite a lot of extensive code given to you. All right, make sure you use the correct code for each studio. Okay, because uh, what we are seeing is sometimes students use earlier code. Okay, without using the latest code, and then there's a mismatch between the way the data is formatted or the protocol used. Okay, and then things don't work. Okay, so you must make sure you use the correct set of code, okay, that is given to you. In most of the applications, the RPi code is given in full, then you need to modify from that. Okay, and then Arduino code, most of it is also given, and then you just need to modify a bit, okay, here and there to fulfill the objectives only. Okay, so let me end here for um, uh, the tutorial questions. Okay, and then let me move over to the review of the sample questions, the midterm questions. Okay, so the sample midterm questions, there are a few of them. So let's go through and discuss them. So in this first question here, we are told that we have a communication system with a baud rate of 9,600. All right, communicated as a sine wave that can be transmitted at 4 voltage levels and 4 phase shift angles. Okay, what is the maximum bit rate in bits per second achievable on this system? All right, so you can see here that currently, okay, what we are, when we say this is the part where we say that baud rate is not exactly bit rate. Okay, that's why we say baud rate is actually what we call a symbol rate. Okay, it's called a symbol rate. Okay, why? Because you are transmitting a symbol which could actually represent a certain number of bits. Okay, now let's just take one voltage here. If I take this one voltage level, that means I transmit, okay, my signal only within 0.0 to 1.25 volts. That means this is 1.25 volts. Okay, so I only transmit at 1.25 volts, but this same voltage range, I have 4 different phases. Okay, phases basically is basically the starting point, right? You start at 0 or 180 or 90 or 270. So that depends on your phase. Okay, that means at 1.25 volts itself, I have 4 different options. These 4 different variations, okay, for the information I can represent. And that also goes to 2.5 volts, 3.75, and 5 volts, correct? So that means for the voltage I have 4 and the phase I have 4. So total I have 16 different variation to how I can represent the data. A total 16 different. So 16 different variations, okay, can be represented using 4 bits, correct? So that means the maximum bit rate is 9600 multiplied by 4. Okay, so that is how you get the answer here is 38,400 bits per second. Okay, so every time you transmit something, you are transmitting an equivalent of a 4-bit data. Okay, a 4-bit data, because you have a total of 16 different sort of symbols that you can represent. Okay, and 16 different symbols can be represented using 4 bits. Okay, so every time you transmit something, you are transmitting what you call a 4-bit data. Okay, so that is again, this question is a good example to show you why we say that baud rate is not actually bit rate, even though we sometimes use that term interchangeably in our system because it is just ones and zeros. Okay, but in reality, communication channels can use a lot of different types of modulation, okay, or protocols where, like in this case, okay, so this is basically what we call uh, a mix of quadrature, amplitude modulation, and phase modulation as well. Okay, that means you're changing the phase and changing the amplitude of a signal to represent different information. Okay, so that's how you get the answer here, 38,400. Okay, then this is okay. So there's a question here: if you can represent 15 different representations. Okay, so if the number of bits, okay, has to be, you need the minimum number of bits depending on what you're trying to achieve, correct? Because if you say 15, 3 bits again will not be sufficient. Okay, so if you have 15 different representations that you want to represent, then you still need minimum 4 bits, okay, of info of per symbol to represent that 15 different types of signals that you have. Okay, so you need to look at the minimum number of bits you need in order to represent that number of symbols you have. Okay, so question two. Okay, so question two is quite a lot of code here. All right. So in this question, you are told that you are implementing a soft serial. Okay, so this soft serial is basically you trying to mimic the behavior of the UART, okay, using software. All right, so that is what this code is trying to do. So you have 2 interrupts, timer 1 and timer 2. All right, and timer 1 here is to do the transmit. Okay, and timer 2 here is to do the receive. Okay, the interrupts. Okay, and over here you can also see the code. All right, where send byte and receive byte. Okay, so there is a typo here. So this is supposed to be 1 millisecond. All right, so there will be an interrupt that will generate every 1 millisecond over here. Okay. Now, so let's look at the code a bit first, all right, and then try to make sense of what is happening. Okay. So for send byte, okay, for send byte, what we are doing? Okay, for send byte, firstly we are doing a digital write low. Okay, this write low is basically to indicate there is a start. Okay, because by write the UART line is high, okay, by default, and then you put it low to indicate it's a start. So this is the start bit, And after you delay for 0.5 millisecond, and then every 1 millisecond, you will generate the timer 1 interrupt. Okay, so every 1 millisecond, you start to generate an interrupt which will send this data. Okay, so the data that is sent, okay, if you look here, you are sending it, okay, the byte to send n with 0x1. So when you say n with 0x1 means what? That means when I take my data, when I do an n with 1, that means I'm only looking at the last bit over here. All right, I'm only looking at this last bit. And this data is the one that is being sent out through a digital write, either high or low. And after that, I do a shift to the right. Okay, so basically when I send out, what goes out first? The LSB goes out first. Okay, and then finally the MSB. Okay, so I'm shifting out LSB first, and then every time I shift, then this shift operation brings the next bit to the last position, and so on until everything is done. And once everything is done, okay, then I pull the line high. This to indicate the stop. All right, so that is what your timer 1 transmit interrupt is doing. For timer 2, okay, for the receive, what is happening? Okay, so for the receive side, you can see that you are stuck in this line digital read 4. That means you are waiting here while it is high. Okay, but the moment it goes low, that means you know that somebody is trying to send you data. Correct? So this is the start bit. Okay, so when somebody tries to send you data, they will pull the line low. So when they pull the line low, you will come out of the while loop and you go to the delay. Okay, so when you go to the delay, you wait for 1 millisecond. Okay, and then after you wait for 1 millisecond, you start with the interrupt here. Okay, so in the interrupt, what you do, you receive data one by one. Okay, but when you receive the data, okay, you can see that you look at what is happening here. You do this operation which is n the bit to write. So what is the bit to write? Okay, the bit to write starts off with 0x80. So 0x80 means the most significant bit is a 1. Okay, and then the bit to write is then shifted right. So I start off with the most significant bit, okay, here, and then I move to the next bit and move to the next bit and so on. So when I receive the data, the first bit that I receive actually goes to the most significant bit and then go on until I reach the least significant bit. Okay, so you can see that the order is reversed in this code. Okay, the order I receive the data and I rearrange the data is different from the order in which I actually send the data out. When I send the data out, I actually send the least significant bit out. But when I receive the data, I put it into the most significant bit first. Okay, so it's the reverse order. Okay, and after that, then then you wait until everything is done and then you end. Okay, so that is again the rough idea of what is happening. So let's look at the options here. Okay, the bits are sampled at a period or at the end of each bit period. Okay, so you can see that the transmitter will wait. Okay, so if I look at the transmitter over here, okay, what will I do? Okay, I will wait. Okay, I will wait for whenever I pull the line low, I will wait for 0.5 milliseconds. Okay, and then I will wait for every 1 millisecond, I will send data out. Okay, so every 1 millisecond, there is some data out. So initially I wait for 0.5. All right. When the receiver, what happened? Okay, the moment the line is full low, he will wait for 1 millisecond. So you wait for 1 millisecond means you come here. Okay, and then he will start to have interrupt every 1 millisecond. That means I will actually be reading, okay, in the middle. Okay, the receiver is actually reading data in the middle of the bit, not in the end of the bit or starting of the bit. Okay, so this is not true. This is not true. Okay, question option 2, the bit rate is 1000 bits per second is true because we are triggering the interrupt every 1 millisecond. Okay, so it's equivalent to 1000 bits per second. So this is true. Bits are received in the bit sent are received in the reverse order. So that is what I just showed you. All right, because of the nature of what is happening. Right, and in the code, the transmit is doing an AND with 0x01, and then I'm sending out. Whereas the receive is doing an AND with 0x80 to write into. Okay, so the order is reversed because of this logic here. Okay, so the bits are received in reverse order. Pin 3, sorry, pin 3 is used for transmit and 4 for receive. All right, so that is, again, you can see it over here, pin 3 and pin 4. Okay, so this is also true. The ground line between two Arduinos do not need to be connected. So this is false. Okay, whenever you have different subsystems talking to each other, they have to have a common ground. All right, so this is again something we have always emphasized before. Okay, so looking at the options, only 2, 3, and 4 are true. Okay. So again, this kind of questions, you need some time to look at it to understand and sort of make sense of what is happening first. All right, then only you can answer the question. Okay, so in this question, we are basically sending the bit pattern, which is this, okay, over 9600 BPS. Okay, so if you look at it, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1. Okay, and so if you want to draw it, okay, so it looks like this: 0, 1, 1, 0, 0, 0, 1, 0, 1. Okay, and now the receiver is sampling set at 4800. Okay, what would you receive? So we have been given you these 4 different scenarios. Okay, so what you need to do is, since I am now going to sample at half the bit rate, all right, so we now need to look at it as 2 bits as 1. Okay, so for this bit, I will now sample in the middle over here, which is a down transition. So this down transition will be sampled as a 1. Correct, so this will represent a 1. Okay, this is a 1, correct, because it is both of it is, both sides of the sampling point is a 1. Here both sides is 0, so it's a 0. Okay, here is a rising transition, so rising is sampled as 1, and this is also a rising transition, so it's also sampled as 1. Okay, so the idea is to make you see that when I sample at half the rate, okay, I am now going to look at 2 bits as 1. Of course, in this case, we have just given you that this transition is now 1 or this transition is 1 and so on. Okay, but practically, we cannot say for sure, right? Because when the transition is happening and the sample is being taken, it could be any value in between. All right, so it may be interpreted as 1 or 0 and so on. Okay, so that is why I mentioned just now that you need to make sure that if the baud rate between transmitter and receiver have to be the same. If it's not the same, the system will still work. You can transmit, you will receive, but when you receive, you cannot make sense of the data, right? Because you're sampling at a different rate, so the data doesn't make sense to you. Okay, so that is again shown here. Okay, so let's look at the next question. Which of the following statements regarding the difference between Rpi and typical PC are true? Okay, so this is quite an old question. Again, things are of course changing very fast, right? In future, this question may not make sense because maybe all PCs may use ARM processors. Okay, but as of now, you can say that in Pi uses ARM processor, and most PCs use Intel processor. So this is definitely true. Okay, for now. Pi does not use a RAM unlike typical PC, so this is definitely false because any computing system that is executing, that is storing code and executing code needs to have some form of RAM. Okay, you need to have persistent storage to hold on to the code. Okay, and you need to have RAM. Okay, to hold on to your variables and your function calls and all this stuff while you're executing code. Okay, so definitely uh, 2 is not 2 is false and 3 is also false. Okay, so the only statement that is sort of true right now is 1. Okay, so only 1 is correct, statement 1. Okay, question 5. Okay, ARM processor or Intel processor. So when we talk about ARM or Intel, we're talking about the processor architecture. ARM architecture is different from Intel's architecture. Okay, ARM's architecture, that means the way the hardware blocks are designed, the registers, the interfacing bus, the data lines. Okay, all of them are different. Okay, so there are two different architectures. Similar to, let's say you talk about AMD, okay, or NVIDIA. Okay, all of them have their own architecture. Okay, in how they design their processors. Okay, and like how the new uh, Apple's M1 as well. Okay, so every processor architecture can be different. Okay, the brand is one. Okay, the architecture could be different. Okay, so it is possible that in the future, uh, Intel may also maybe merge with ARM, correct? And then they will start to integrate ARM core inside their processor. Then of course, then all this will change. Okay, but for now, there are two different processor architectures. So when you say it's ARM processor or Intel processor, we say it's two different architectures. Okay, so for this question here, what we are trying to do is we are given an array of n unsorted numbers, and we want to find, okay, whether there is any pair that adds up to a target value s. All right, so we have given you some possible options here. So the first option is if we solve the pair sum problem by exhaustively trying out all the pairs. Okay, that means you have a dual nested loop here, and then you try to solve, okay, whether any of it is equal to s. Okay, is one possible way of solving it. Okay, well, of course, the dual nested loop, the nested loop basically tells us that the order will definitely be n squared. Okay, so the answer for this is e, which is n squared. So that part I think is quite clear. The part 6 here is we are solving it using bubble sort, and then we do a binary search. Okay, a bubble sort and binary search. So for bubble sort, we know that the order is n squared. All right, so the two possible answer is here, okay, or here. All right, now for phase B, binary search. So for binary search, basically means what? That means if you remember a binary search, you are basically doing like a divide by 2 each time, right? Because when you say binary means you have a tree, okay, and then you divide, okay, and then you divide, and then you divide, and so on. So whenever you are doing this divide by 2, all right, continuously, you already know it's log 2n. Okay. Now, when you divide by 2 all the way, there's uh, there's high chance you may go all the way until the length which is at least half of the n elements, all right? Because you may need to search one complete half, all right, until you reach the final one that you want. So this depth here could be n by 2. All right, so n by 2, if you generalize it, it become n log n. Okay, so that is why the answer for this is C. Okay, so again, is very similar to what we have been seeing in our earlier tutorial questions as well. Okay. For last part here, if you modify the solution, okay, so bubble sort first, and then we look at this approach where we have two index. Okay, so after I do a bubble sort, I have two index, left and right. Okay, and then what I do is I try to check, okay, whether it's possible. Okay, if it's not, then I look at whether the number is bigger or smaller, and whether it's bigger or smaller, I decide to either increment this or decrement this. Okay, so I keep on doing it in a loop. All right, so in this case, you can see that the worst case scenario is I will complete the entire uh, array, okay, which is the order of n. That means depends on the size of the array, order n. Okay, so the answer here is C, because the order here is depends on how big the array is. All right, so that is the answer for this question here, question 7. Okay, so question 8 is on Git. So in Git, the question is on staging. Okay, so let's look at the options to see if any of them are true. The first option here, if a file is already being tracked by Git, there is no need to stage the file to commit new change. Okay, so it comes back to the idea of staging. So what is staging? Whenever you say you want to commit, all right, that means you always need to stage the file first and then you commit. All right, so that is a standard process. So even though it's being tracked by Git, all right, when you want to commit, you must stage. So that's always the first step. You need to stage first and then you can commit. All right, so if you don't stage it, you cannot commit the file. So that is not true. Okay. To add a new file for Git to track, there is no need to stage to commit new change. So again, this is again similar to the first option here. Okay, whenever you want to commit, you must stage. Okay, so that is the standard process. Okay, part C, we always need to stage all modified files before committing. Okay, so the key thing is this all modified files. All right, when you are working, okay, on your system, on your code, you may modify a lot of files. Correct, but you may choose to only commit some of the files, okay, because some of the other files maybe you are still thinking about the changes and making some improvements and so on. Okay, so you can work on a lot of files, you can modify a lot of files, but you can choose to only commit some of them. So you only need to stage those files that you want to commit and then you commit. Okay, so you don't need to stage all the modified files. If you stage all the modified files means that means you want to commit all of them. But it's not necessary. You can choose to stage some of the files and then commit them first. And then the other files, you may still be working on it. Okay, so this is not true. Okay, forgetting to stage a file will cause merge conflict. Again, it's not true because if you don't stage a file, okay, it will not be committed. Correct? You will only commit, okay, when you commit, you already have staged it. So when you push it, okay, you will cause a merge conflict if there is a issue with the current version that's already being committed earlier. Okay, so when you forget to stage, that means basically you will not commit it at all. That means you will not push it in. So there's no way it can cause a merge conflict. All right, so none of the statements here are true. Okay, all of them are false. Okay, so that's why the answer here is E. Okay, none of the above. Okay, question 9 here is on the interrupts. Okay, so which is or the following is correct? All right, so let's look at this. So for part A, detect interrupt, get address of ISR, execute ISR, pop PC from stack, push PC from stack. Okay, if you detect interrupt and you straight away get address and start executing without saving where you are, that means currently where you are executing in the main code, then later on you can never come back to the main code. All right, so definitely this is not true. Okay, get address of ISR, detect interrupt. Okay, so again, this first two steps is already written in the wrong order. You first must be able to detect that there is an interrupt. Then you get the address of the ISR. Okay, so you cannot get the address of ISR before knowing that or before detecting that there's an interrupt. Okay, being triggered. Okay, so B is not true. C, push PC onto stack, detect interrupt. So again, you do not push PC onto stack without even detecting there is an interrupt, correct? You go through the process of pushing the PC only when there is an interrupt being detected, then you need to stop what you're doing. Okay, so C is not true. Detect interrupt, get the address of ISR, then the push PC on the stack, execute ISR, and pop PC on the stack is correct. Okay, why? Because the first step is always you want to detect the interrupt. So the detecting the interrupt is you have already configured the registers accordingly. So if you look at each peripheral block, timer, UART, GPIO, for each of them there is some interrupt enable bit somewhere. Correct. So if the interrupt enable bit is configured and globally you've also enabled interrupt, so when that event happens, that hardware event happens, you will automatically detect that this has happened and will send a trigger to the processor. Then you will be able to go to the interrupt vector table to get the address of the ISR. Okay, inside the interrupt vector table is where you store all the addresses of all the various interrupt service routines. Okay, so once you get the ISR, then you can push your current PC onto the stack, then jump to the new ISR. Jump to the ISR and start executing it. And then when you finish, you pop the PC from the stack. Okay, in part E, you detect interrupt and then you pop PC on the stack. So again, this doesn't make sense, all right? Because you only pop from the PC from the stack after you finish the ISR. Okay, so this is not true. Okay, so the correct option here is option D. Okay, based on the sequence that we know. Okay, what happens when you detect an interrupt? Okay, so in question 10, we have two buttons A and B connected to INT0, INT1 respectively. Okay, both of them are triggered by the rising edge, and both of them already been enabled. Okay, so what would happen if both of them are pressed at exactly the same time? Okay, so let's look at this. So I have A and B. Okay, so A, so I think it's not clearly written here. Okay, A is connected to interrupt 0, B is connected to interrupt 1. Okay, so let's draw the line. So I have A and B, and let's assume that at this point of time, both of them are triggered. Okay, both of them trigger the rising edge. But what happens is, let me see the question again. They release B before releasing A. So after I press B, I release first, and then after a while, then A is released. Okay, release B first before releasing A. Which statement best describe what will happen? Okay, so the first thing you must know is, if you recall, by default, there is nested interrupts are disabled. That means when one interrupt is happening, the other interrupt has to wait. Okay, and the other thing is the priority of interrupts. So the priority of interrupts is the order in which they are arranged in the vector table. So if you look in the vector table, okay, you'll see the INT0 is higher priority than INT1. Okay, the INT0 comes first in the table. Okay, so when I'm running my main code, okay, when I'm running my main code, I will run, and then when both of them happen at the same time, I will jump to INT0 first. I'll finish what I need to do, come back, and then I will jump to INT1. Finish what I need to do, then go back, and then I carry on. Okay, so when I go to INT0, what will happen? When I go into INT0, turn is 0. So I will do flash rate. Okay, and after that, okay, when I finish the interrupt, okay, I will straight away come to INT1, and I will say turn is 1, so I will flash green. Okay, so I will momentarily flash red, and then I will flash green. Okay, so it does not matter when I release. Okay, this duration here has no impact because this has nothing to do with the interrupt. The interrupt is triggered because of the rising edge. Okay, so when the rising edge happens, I will jump. Okay, it's a matter of where I go first. Okay, so INT0 is higher priority, so I go there first. I change turn to 0, and then after that I'll straight away go to INT1, and then I'll change turn to 1. Okay, so this is the sequence. Okay, so the correct answer here is C. Okay, and this is the multiple response question. Okay, sample. In fact, just now also we saw one sample, correct? Was there a sample just now? Oh no, just now was all MCQ, correct? This is the MRQ. Okay, so in multiple response question, okay, so if you see a full marks will be given if all correct answers and no wrong answers selected. If only some correct answers are selected or any wrong answer selected, you will be given partial credit. Okay, so you need to look carefully to see what are all the possible answers. So in this question, basically, we are given that we have an Arduino with a 16 megahertz clock. Okay, timer 0 is configured for Ctc mode. Okay, with OCROA value at 249. Okay, and timer interrupt is enabled. So which are the following valid intervals? Yes, the valid intervals. So in this case, what you need to do is you need to check. You need to look at all the possible prescaler values. All right, so the value prescaler values again you can calculate, and for each of the prescaler values, okay, if I were to count up to 250, correct, 0 to 259, okay, and with each of the resolution that I get after the prescaler, what are the possible intervals that I can trigger? Okay, so you can see that the possible intervals I can trigger, okay, from this case are 1, 2, 5, and 4. Okay, so this calculation is again similar to what we saw, so it's just 1, 2, 5, and 4. So the two possible answers here are B and D. Okay, so yeah, I think so. That's the last question here. Okay, from what is given to you. Okay, so so far any questions that anybody have? Okay, so let me just quickly go through the SOP for tomorrow. I hope you have gone through this. Okay, so in this SOP, uh, again there is a link here, but I'll not go through the link. Okay, make sure you have installed the screen recording software. Okay, to record your screen, and of course make sure that you also have sufficient storage. Okay, to save your screen recording. Okay, Zoom must be installed. Okay, uh, on your phone. Okay, for you to make sure that you are able to position it. Okay, and put it in a way that it captures you as well as the screen. Okay, so I think all these are quite standard. Most of you have gone through this before. Okay. Okay, so F says that you're not allowed to use wireless devices. Okay, for the test. Okay, and we will be using luminous quiz. Okay, so that part is already known. Okay, the timings are very important. Okay, you are expected to log in early. All right, to uh, give time for the setup and for the TAs to check everything, okay, and make sure that your camera angle, your lighting, everything is good. All right, so please follow the timings given so that you are able to or the TA is able to check everything and set up everything properly before we start. Okay, so there are no breaks allowed during the exam. Okay, and the quiz is on Luminous. Okay, password will be issued. All right, uh, when only when we're going to start. Okay, the timing will begin the moment you key in the password and you click on start. All right, so we will only give you the password. All right, when we are going to actually start the quiz. Okay, so we'll not give it earlier. And the Google Forms. Okay, so the Google Form links, please make sure you open up and you look at it regularly. Okay, because that is where you are able to ask questions and also see the replies. Okay, so there's some protocol here on how to ask questions. Please follow that. Uh, so you need to make sure you phrase questions in a way that they can be answered with yes or no. All right. Uh, sometimes the way you ask the question, you may really be hinting at some possible answer. Correct. So you may not be able to share that question. Okay, on the Google form. Okay, so you need to answer in a way whether very specifically what is the thing you want to clarify. Okay. Again, uh, if it is something that we cannot answer, all right, because it maybe something you are expected to know, then probably we'll just say no comment. Okay. And if your question cannot be answered in a clear way, then we will ask you to rephrase. Okay. So again, if you have questions, you can ask, but again, be mindful that ask the questions in a way that you are clarifying anything that is you feel that is not clearly explained in the question. Okay. Uh, yeah. So again, Zoom connection sometimes yes can drop off. Okay. Can go off and so on. Okay. You have to make sure that if anything happens, you are able to quickly reconnect. Okay. So your phone, please make sure it's always plugged in, it's charged, it doesn't go to sleep or anything like that. Okay. Again, once the timing ends, the quiz will also automatically close. Okay. Uh, yeah. So again, once the exam is over, please remain. Okay. And then or the invigilator will tell you when you can go off. Okay. So this is the backup plan. Okay. In the event that Luminous quiz has some issue and can't carry on with that option, then we will issue you the PDF file of the quiz questions. All right, and you're supposed to complete the quiz in a Word document. All right, so in a Word document, you're supposed to key in all your MCQ answers. All right, and name your file accordingly, and then email your answer script. Okay, within 5 minutes of the deadline. So again, this is only the backup plan in the event that there is an issue with Luminous. If not, we will carry on with Luminous. And after everything is done, okay, you by 5 p.m. you're supposed to upload your screen recording. Okay, so please ensure that you do that. Okay, so again, uh, you're only supposed to upload the link. Okay, not the full screen recording, only the link. Okay, within by 5 p.m. that day. Okay, so these are all the guidelines. Okay, so maybe some of it is similar to what you've done before. Some may be a bit different or a bit new. So just make sure you have gone through everything and you're familiar with all the guidelines that we have for you. Okay, so I hope all of you are prepared. Okay. Okay, so I will not hold you all back any further. Okay, because I think we covered all we need to cover, and probably we also want to do some last minute catch up with everything. All right. So that's all we have for today. All the best for tomorrow. Okay, so please wake up on time. There's always a case where somebody will oversleep. Okay, and then we are trying to figure out what happened to the student, and then they will join in 15 minutes late, 20 minutes late, and so on. Okay, so if you can, probably ask one of your friends to give you all a call, call each other, just to make sure everybody wakes up, okay, on time and is ready. Okay. Other than that, I don't have anything else. If you have questions that you want to ask, you can stay back and ask. If not, that's all. And good luck for tomorrow. Okay. Sleep early. Okay. Have a good rest so you can do the paper well. Okay. Thank you and good luck. Okay. I'll see you all tomorrow.